Every NVIDIA data sheet is designed to make you feel like you need the biggest, most expensive version of whatever they're selling. The H100 spec sheet is no different. There are numbers on there that matter a lot, numbers that matter a little, and numbers that are basically marketing. I'm going to walk you through which is which. The H100 is built on the Hopper architecture, NVIDIA's GH100 die, fabbed on TSMC's 4N process. It's 80 million transistors on an 814 square millimeter die. For context, the A100 was about 54 billion transistors on a smaller die at 7 nanometers. You've got 16,896 CUDA cores and 528 fourth generation Tensor cores. The CUDA cores handle your general purpose compute. The Tensor cores are the ones doing the heavy lifting for AI workloads. Matrix multiply operations at mixed precision. But the number that everyone overlooks on this chip is the L2 cache. It's 50 megabytes. The A100 had 40. That's 10 extra megs, meaning more of your model weights and activations stay on die instead of round tripping to HBM. For inference especially, that's a real throughput gain that doesn't show up in the TF-flops headline number. I cannot stress this enough. The SXM and PCIe are not the same product. They're with a different connector. They are fundamentally different performance tiers. Both have 80 gigs of VRAM, same capacity, but the SXM uses HBM3 at 3,350 gigabytes per second of bandwidth. PCIe uses HBM2E at about 2 terabytes per second. That's a 68% gap. For any workload that's memory bandwidth bound, which includes most large language models and a lot of inference at scale, the SXM is in a different league. The other massive difference is interconnect. SXM gets NVLink 4.0 at 900 gigabytes per second, GPU to GPU. PCI gets PCI Gen 5 at 128. That's a 7x difference. When you're doing distributed training across 8 GPUs in a node, NVLink is what keeps your scaling efficiency high. Without it, your GPUs spend more time waiting on each other than computing. The trade-off is power and infrastructure. SXM draws up to 700 watts and requires an HGX or DGX baseboard. PCI is 350 watts and fits in standard servers. If you don't need multi-GPU training at scale, PCIe saves you a lot of money and complexity. Now, when you hear about InfiniBand and Ethernet backbones, that's going to be your SXM models. That DGX and HGX baseboard allows for networking between the GPUs and the GPU nodes that you simply don't get with PCIe. If I had to pick one spec that separates the H100 from everything that came before, it's the Transformer Engine. There's dedicated silicon on the tensor cores that dynamically switches between FP8 and FP16 precision on a per layer basis during training. It looks at each layer of your transformer model and decides whether it can get away with 8-bit math without losing accuracy. If it can, it runs at FP8 and you get double the throughput. If it can't, it stays FP16. That's why NVIDIA's headline claim of 4x faster training than A100 isn't just clock speed marketing. The Transformer Engine is doing fundamentally different math. The A100 couldn't do FP8 at all. Its floor is BF16 or FP16. The one thing to be aware of, that 3,958 T-flops FP8 number on the spec sheet is with sparsity. Most production transformer models don't have 50% sparsity in their weights. So in practice, you should think of the dense number, roughly half that, as your realistic ceiling. Still a massive leap over A100, but just know what that asterisk means. Now, memory, 80 gigs of VRAM. There's no 40 gig H100, unlike the A100, which came in both in 40 and 80. So what does 80 gigs actually get you? In FP16 with no quantization, you can fit roughly 30 billion parameter models. At 4-bit and 8-bit quantization, you can run a 70 billion parameter model. Something like Llama 2 70B. If you need to get bigger without quantizing, you're looking at a multi-GPU setup where NVLink becomes critical, or stepping up to the H200 with 141 gigs of HBM3. For most production inference serving today, 80 gigs is plenty. It's when you start pushing model size boundaries that you need to think about whether to go multi-GPU on H100 or single GPU on H200. Right. Multi-instant GPU. One more spec that matters if you're running multi-tenant inference is MIG. That's multi-instance GPU. The H100 can be partitioned up into 7 isolated instances, each with its own dedicated memory cache and compute cores. Hardware level isolation. One tenant's workload literally cannot interfere with another's. Now, why this matters. If you're serving inference to multiple customers or running different models side by side, you don't need to dedicate a full H100 to each. You carve it up. Single H100 can serve 7 lightweight inference loads simultaneously with guaranteed QoS. Now, if you're building a GPU as a service business, which a lot of mining operators are evaluating right now, MIG is how you turn one expensive GPU into a multi-tenant revenue-generating machine. All right, so a quick comparison with the A100, because this is the question we get every day. Memory bandwidth is 64% faster. NVLink is 50% faster. FP16 tensor over 3x. That's the H100 that has FP8, and the A100 doesn't have that at all. For transformer workloads, the real-world gap is 3 to 4x in training throughput and 2 to 4x in inference, depending on model size and batch configuration. That lines up with what you see from buyers running both. And we have a dedicated H100 versus A100 video if you want to see the full breakdown. Link will be in the description. But just know, if you are running an H100 as a GPU as a service provider, you will get a higher hourly rate than A100. Now, those are the specs that actually matter on the H100. Next in the series, we're covering which workloads are best suited for which and which ones you might want a different GPU for. Links are below. If you're comparing GPUs for a real deployment and you want to talk through options, hit up our hardware team at sales@luxor.tech.